Okay, hey, so let's come back to our little wall example here. And what I did is just, I created a single brick, and with a couple of copy and transforms, I create this wall. So what we want to look at now is how we can constrain this. So how can we basically glue those bricks together? Because so far what we've looked at are constraints that come out of a side effects node, for example, the Voronoi fracture. So if we took this box here and we fracture it, then what we get is basically those constraints for free. But what if we have a geometry like our wall here that we have to kind of glue together ourselves? What we do then? Well, there is a node that helps us with that. When you type in RBD constraint, you get a couple of RBD constraints from nodes. And there is an RBD constraints from curves, RBD constraints from lines, and RBDs constraints from rules. I decided not to explain the RBD constraint from curves and from lines. You can have a look at that yourself. But I found in most cases you use RBD constraints from rules, and this is what we mainly want to look at. So the RBD constraint from rules, if I just plug it in, basically finds all the pieces in our setup here and connects them automatically. If you just connect them, unfortunately you get an error, and which is what's really annoying is that it doesn't actually tell you what the error is. The problem is that it looks for a name attribute, and currently we don't have that. And you can see that here in the piece attribute called name, this is what it's looking for. To create this, of course, we can just use an assemble, and by default that's all it needs, and right away the node works. So let's have a look at the constraints we get out of this. And they look like that. And this is great because that's all we want. So it finds all the pieces and connects them. Now, what we can do with this, for example, is I prepared a little setup with a sphere here that is animated. Whoop. And if I connect this, of course, to our constraint, to our solver collision input, and then make sure that it is a deforming static object, then what we get out of this is this here. So pretty much what we need. We will have a look later on how to make sure that the wall doesn't just fall over once it gets hit by the sphere. But for now, all I wanted to show you is, as you can see, all the pieces stay together. Yeah, okay, and then they fall over. But they are glued together, and we can do this with any geometry we want. This is really all you need to know. This node, RBD constraint from rules, but let me quickly show you a problem with that, and that can occur sometimes with a bit more weird geometries, or just geometries where the distances between the center of the pieces is further away. So what comes out of this looks like that. So we get only a few connections. It doesn't find the connections between the bricks on the vertical level. And the reason is a couple of things, actually. There is a certain search radius. And now you say, okay, fair enough. I just increased that. And it actually does find more connections. So that's fine. That's a good solution. But certain connections it still doesn't find. For example, up here, those ones. And you have to understand a little bit how this node works, because it's not that intuitive. What you think it does is it looks for the center point and looks for the closest ones, but that's not actually what it's doing, because that would mean that, as you can see here, the distance between those 2 points is much higher than the distance between those points. And what we actually want to glue together is not the center, but here, this geometry here. So let me quickly show you that this is actually important. If I increase the scale of my brick and make it just wider, you can see that it all of a sudden finds connections. So even if I lower, and that's a funny thing, even if I lower the search radius back to 0.1, I can show you that this is actually important. As you can see, it finds the connections not based on the distance between the center points, but actually based on the distance between the surfaces of the geometry they represent. This is quite important. Why? Because you have to understand how it does that, because it does that in a pretty weird way. What it does internally, it scatters points on the surface. This is here points per area, and then it finds the connection between those points. Why is this important? Because it sometimes doesn't behave as you would think. So let's break this again, and let's make sure we increase the search radius, which worked for us before. but it doesn't find all the connections. For example, up here, the connections aren't found. So even if I go higher and higher and higher with this, it doesn't work. Now, the weird thing is you would think, let's increase the points per area. And I would agree, that would be logical. But as you can see, that makes it even worse. So what's going on here? For some reason, you must lower the number. And this is actually explained in the mouse over, that you should lower the number when you increase the distance. To be honest, I can't fully explain to you why that is. It doesn't really make that much sense to me, but because of that, I explain to you what you have to do. So to find all the connections, sometimes you also have to increase the max connections and lower the points per area. Let's see what happens if I lower this to 1, weirdly enough. And you can see it finds more and more connections. So while the search radius increasing that makes more findings, and also max connections, which means max connections between points, also increase the findings. What is not intuitive is that you have to lower the points per area. So let's go back to the default of 100, and we can see it actually finds less. Let's increase that further, and it finds less and less and less the higher the points per area is, and it gets actually quite slow. So for some weird reason, you have to lower it to 1. At the same time, that's not true if you have a low number in the search radius. When you have a low number in the search radius, you actually do have to increase this number. And 100, for example, was then a good solution. Let me quickly make sure we have something normal again. So with a lower search radius, lowering the point area is actually not the solution. So those two, points per area and search radius, are inverted, so to say. They are the complete opposite. So again, if you increase that number, you have to lower that number. If you lower that number, you have to increase that number. Not very intuitive, but that's why I show it to you. Okay, so this is how RBD constraints from rules work. Play around with this if you have a connection problem. To be fair, very often when your pieces are very close together, for example, you should not have this problem. So in this particular case here, this worked by just plugging it in, and if it works, that's fine. Okay, so that's the RBD constraints from rules, and it's a great way, even though sometimes it behaves a bit weirdly, to create your own constraints from whatever geometry you have. All right, hope this was helpful. Thanks very much. See you later.